It's working, sir.
I'm sorry. I do not know why it didn't work yesterday. I didn't do anything different today than yesterday. Something must
Only
have changed.
center you need to click that window, sir. Then that share button will highlight. Center of the screen.
Yes, yes. So this time I just shared the window so that I could just share the
Okay.
PowerPoint, which is what I've
Okay.
done in the past. Again, I'm
Okay.
sorry. I, I wish I could tell you what I was doing wrong, but obviously I was doing something incorrectly. I don't
Okay.
know what.
Yeah.
So,
Yes, sir.
all right, we'll start in about 10 minutes. Is that
After
correct?
10 minutes. Yes, sir. 10 minutes, sir.
Okay. All right.
ఎక్కువ కనిపిస్తున్నా ఒకసారి నాదే చూపిస్తారా? Sir, good morning, sir.
Good morning.
Shall we start the program, sir?
Yeah, whenever you're ready.
Yes.
Can you hear me all right?
Yes, sir. Yes, sir.
Okay, very good.
Yes. Good morning to all the participants. I welcome you all for the second day of our online workshop on urban storm water management, which is going to be organized by the Department of Civil Engineering, Andhra University College of Engineering, Visakhapatnam. The workshop has been sponsored under the TechU Phase 3. And today we are going to start our first technical session of the workshop with Professor S. Govindaraju. So meanwhile, before we'll start our technical session, I would like to give you a brief introduction about the Professor Govindaraju. Professor Govindaraju is the Bowen Engineering Head and the Christopher and Susan Brooke Professor in the School of Civil Engineering at Purdue University. Also, he has been appointed as a visiting professor to the Andhra University Civil Engineering Department. He earned his PhD in Civil Engineering from the University of California, Davis in the year 1989. His primary areas of research include surface and subsurface hydrology, contaminant transport, watershed hydrology, and climatic influences. He is interested in developing algorithms for analyzing and learning from hydrologic data. He specializes in problems dealing with uncertainty and spatial variability. His research work has been supported by various agencies such as NSF, EPA, DOD, and DOE. He has chaired national level committees and has served as the editorial boards of several journals. He is currently the editor-in-chief of Journal of Hydrologic Engineering, American Society of Civil Engineers, and served as the president of American Institute of Hydrology. His work has been recognized with numerous national and international awards. Dr. Govindaraju has co-authored 4 books, 25 book chapters, over 145 referred journal articles, and delivered 60 invited and keynote presentations. He has advised 15 PhD students, 22 MS students, and worked with 11 postdocs and visiting scholars. Recent awards includes the ASCE Venti Chow Award and the AIH Founders Award. Now I take the pleasure of inviting Professor Govindaraju to deliver his second lecture on runoff competition. Thank you, sir.
Thank you. Just a minute while I bring up my presentation here.
Yes, sir.
Can you see my screen now?
Yes, sir.
All right. Well, let's get started. Thank you, Suyapati, for the introduction. So in the next hour or so, I want to talk about runoff estimation methods. And these are some of the methods that are used for design in some places. So it's going to be fairly basic stuff, nothing that approaches research. The topics that we will cover are essentially going to be dealing with runoff. And I'm showing some pictures over here, very similar to what you saw in Professor Uma Mahesh's slides when he was speaking yesterday. We want to minimize the adverse effects of flooding by trying to manage stormwater, and therefore runoff computation becomes important. We will start with defining some terms. Watershed delineation, I will not talk about it because I expect everybody knows about it. I want to briefly talk about the rational method, and in doing so also visit the idea of time of concentration, which is part of the rational method. I'll talk about the SCS curve number method for partitioning rainfall into effective rainfall and abstractions, and then perhaps talk about the unit hydrograph theory, which allows us to translate effective rainfall into direct runoff. So,
Sir,
yes?
Sir, small request. You can make it full screen, sir.
Actually, it is full screen right now.
No, sir, it is not full screen.
Just a minute. It is not full screen. It's
Yes.
How about now? Is it full screen now?
So far, it is not activated, sir.
Okay, I see it as a full screen. It is not for.
Sir, you can make it a slide share, sir. Slide share at the bottom, you can see. Yes, sir.
That's what I'm doing. Can you see full screen now?
No, sir, in the same position only.
Okay.
Okay.
Let me, should I try and log in again?
No problem. No problem, sir. You can continue it, sir.
Well, it is a problem because I am seeing full screen and you are not. So let me do this again. Let me log out and come back in. This is, so it will take me a minute. Let me log out and come back in and try again, okay?
Okay. Slide share. Sir is clicking the same one. Sir, please unmute yourself, sir. Yes, sir.
How about now? Is it full screen now?
Same as the previous one, sir. No problem, sir. You can continue it, sir.
Okay, then I do not know what again the problem is. This is curious. All right, so runoff estimation. Okay, let me know if you can see the laser pointer. Can you see the laser pointer?
No,
Hello?
sir. No, sir.
Yeah, because the laser pointer, I see it on my full screen, so you're not seeing it. All right.
Okay.
So Well, I wonder if I need to exit full screen then, because I don't know what you are seeing.
Sir, you can increase the percentage, sir. Percentage now it is in 60%. You can make it at least 100%, sir. Yes.
Okay.
Okay, sir.
All right, we will try this, I think, and see. So let's start with the rational method. And so the rational method is a simple formula. It's one of the simpler methods. Let me adjust this because it's still not coming from my screen. Okay. The rational method is a simple formula which says that peak discharge rate, peak runoff rate is going to be a runoff coefficient C times the design rainfall intensity I times A, which is the contributing area of the watershed, and K is a quantity that we adjust for units. And the rational method is recommended when the area is, the contributing area is less than 200 acres or 81 hectares or so. Are you able to see the slides? Hello?
No, sir.
Yes, sir. We can see it, sir.
Well, somebody said no.
It shows half screen.
It's half screen. Yeah, I mean, even on my screen, I cannot see the full thing.
Means percentage you can get.
How about now?
Okay, sir.
Well, still don't know why. Okay, so this is the rational method, and C times I times A. So assumptions of the rational method are that the return periods that we have for peak discharge, which is what we are trying to calculate, we assume that the peak discharge return period will be the same as the design rainfall return period. So we basically prescribe the return period to rainfall, calculate the peak discharge for a design event. The rainfall is assumed to be spatially uniform. Storm duration associated with the peak discharge that we want, that is set to the time of concentration of the drainage area. So we need to talk about the time of concentration because the design rainfall will get its duration from this time of concentration. The runoff coefficient we assume is not influenced by return period, and it's independent of storm duration, watershed infiltration rates changing with time, soil types, antecedent soil moisture content. All of those have to be captured in this one runoff coefficient. The rational method may be used only for design storms. And what we typically do is look at tables to see what the runoff coefficient should be. So this is a table that is typically used for rural areas, and similarly another table or other tables for urban areas, as you see. And depending on the description of the area, we pick a runoff coefficient within a range. And if it's a composite area, mixture of urban and some rural areas, we look at different sets of tables to get the value of C, the composite, the runoff coefficient. So getting this runoff coefficient then is where the designer's experience or the modeler's experience has to come in. But it tries to encapsulate a lot of things. And so it's an approximate method. So if we look at the calculation now, K is basically going to depend on unit. I, calculation of I, the design rainfall intensity, whether it's centimeters per hour, inches per hour, that requires frequency or a return period to be specified. So many years, a 50-year event or a 100-year event. This is typically dictated by design guidelines and regulations. For the design rainfall I, we also need to know the duration of the rainfall event for the design rainfall event. And that is equated to the time of concentration for the watershed. So again, time of concentration computations become important. There are many travel time formulae that are used for calculating the time of concentration. I'll share just one of them, the FAA method, since it's still fairly commonly used. Even though this method was originated in the 1970s, it's an empirical method which gives you a way of calculating travel time for overland flow. K is again used to adjust the units. C is the runoff coefficient from the rational method. L is the distance of travel. And S prime is the average slope along this travel distance. So most travel time formulae will involve a travel distance, a slope, and another factor like the runoff coefficient or what have you to account for surface properties like surface roughness. The more common method that is used for many designs, especially in rural and let's say suburban areas, is called the TR55 method. And the TR55 method essentially does calculations for travel time based on, let's say, a watershed as shown over here. And let's say it has a small stream and A is a design point where we are trying to estimate a peak discharge for a design rainfall event. To calculate the time of concentration, the TR55 method basically conceptualizes 3 different pathways before water will reach this design point A. We first identify what we think would be the hydraulically most distant point on the watershed, which is given by this green location. We think the travel time for water falling on this watershed at this green location, that will have the longest travel time to get to point A. The first part is sheet flow, where water is flowing as a thin overland sheet. This sheet flow is maintained at most to a distance of 100 feet, after which water will start flowing in shallow concentrated flow through rills and gullies and concentrated flow paths until it reaches a recognizable channel, in which case you see segment 3 over here, which is channel flow. For the sheet flow travel time, we have an expression given over here. So this is an empirical equation. N is the Manning's roughness for this sheet flow region. L is the length of that flow path. P sub 2.5 is the 2-year 24-hour rainfall depth, and it's raised to the power of half. So P2 is a 2-year 24-hour rainfall depth. So this is a design rainfall. And S is the slope over the sheet flow part. So depending on the length of flow for sheet flow, we would use that length over here, but this length cannot be greater than 100 feet. Then for the second part, when we have shallow concentrated flow, we essentially, so beyond 100 feet, sheet flow will become concentrated flow. Velocities and travel times are determined by the watercourse slope and the type of surface. So in the next slide over here, we use a graph of this nature based on the nature of the watercourse, whether it's a paved or an unpaved area. We essentially see what slope it is at, come to horizontally, whether it's paved or unpaved, come down and pick a velocity. Once we have the velocity, we use that velocity over here. Travel distance along pathway 2 divided by the velocity gives us a travel time. So that's a second travel time. The third travel time is when it's essentially moving as channel flow, in which case we use Manning's equation. So the blue region is essentially where we have channels. Sometimes we may split these channels into smaller sections of homogeneous properties and calculate the travel time through each of these homogeneous sections, where we calculate the velocity using Manning's equation. We assume uniform flow. So S is the slope of the channel bed. And then we calculate the travel time through the open channel segments. And as I said, if we need it, we will split the channel into multiple segments to calculate the travel time. So the time of concentration, that is for mostly, as I said, for rural areas. For urban areas, we don't have a watershed that is delineated based on topography and stream network. It's primarily determined by the sewer network that we use, and we design the sewers to collect water from certain areas, and that becomes a contributing area. Again, travel time is again used as the same definition, travel time for the most hydraulically distant part to contribute to the point under consideration. And so that will include overland flow travel time plus gutter flow travel time plus travel time through the sewers. And the overland flow travel time is very often replaced by what we call as inlet time. So it's time for water to flow over wherever it lands, to flow over the land surface to the first inlet that takes it to the sewer system. And this is typically assumed between 5 and 20 minutes. Once the water does reach a sewer, we are able to design them so that we know what the velocities are or what the flow rates are. And then the sewer flow travel time is simply the distance or the length of the sewer divided by the velocity. So time of concentration becomes important for the rational method. Okay. So I have decided not to do an example over here for the rational method in the interests of time. I'll just list the steps that are used in the rational method. So we first determine the contributing basin area A from appropriate maps. We estimate a composite C value depending on the contributing area. If the contributing area has different land uses, different soil types, then we partition the area into, let's say, small n sub areas. For each of these, we find the runoff coefficient, and then we compute a composite runoff coefficient. We determine the time of concentration, typically using the TR55 method or any other method that's available to us. Once the time of concentration is known, then we compute the design rainfall intensity from an intensity duration frequency relationship. The duration is set equal to the time of concentration at the design point, and the return period, as I said, is governed by regulations. So once we have that, we compute the design rainfall intensity I, let's say from a regression equation, and then we use this expression for computing the peak discharge. And then if we go to downstream locations in the stream network, the contributing area will change, and the travel time is computed based on knowing the travel time to the upstream point, and then figuring out what pathways are there that bring water to the downstream point and comparing them. So the rational method is something that is quite often used for design. It's the simplest method that we have. Okay. The next method I wanted to talk about is the curve number method. Shivaparthi, do you want to wait for questions until the end, or should we take a break and take questions?
Sir, we can take the questions at the end of the session, sir.
Okay, all right. So the NRCS curve number method is essentially a step towards a better method in some sense than the rational method. The rational method has many limitations. It is simple, so it's popular, but it's one of its limitations is, of course, that it can only be used for design rainfall events. It cannot be used for any real rainfall events. And then, of course, as I said, with one runoff coefficient, we try to encompass a lot of what is happening in hydrology. The curve number method, to start talking about it, I've drawn a series of figures over here. On the left is a typical rainfall hydrograph. So if we have a rain gauge and we are collecting data as a function of time, let's say this is the rainfall intensity in inches per hour that we have as a function of time. Okay. And so the rainfall intensity can be varying with time. And this is the total rainfall that we have. What we would like to do is, of this total rainfall, only a small part or only a fraction of it is available to move on the land surface as surface water and create runoff. Some of it is essentially held back in the soil as abstractions. So abstractions would include depression storage, infiltration, any losses that we have from the rainfall. So abstractions or losses need to be taken off. That water may reach the stream, but it reaches there first by joining the groundwater, becomes part of base flow, and very slowly, perhaps over a period of months, will reach the stream. That is not what's going to create a flood. The rainfall excess water is what we need to manage. So if we have a given rainfall event, let's say it occurs over a watershed, and we are interested in figuring out what is the flow rate that's coming out because of this rainfall event, we therefore need to partition the rainfall into the excess part or effective rainfall and abstractions. And that is what the curve number method allows us to do. If we are observing stream flow, let's say at this outlet, and we have a stream hydrograph, then because of this rainfall event, the hydrograph will have particular properties. The base flow part is that amount of flow that was already existing in the stream at this location, even let's say before the rainfall event. And because of this rainfall event, there is going to be a rise in the stream hydrograph. And after the rainfall event is over, perhaps the hydrograph or the flow discharge goes down and eventually reaches its value that it had before the rainfall event. And if we can separate the stream flow into base flow and the part that's directly responsible or directly responsive to this rainfall event, we would call that as direct runoff. So the curve number method works with this portion. It takes the rainfall and partitions it into effective rainfall or rainfall excess and abstractions or losses. Okay. And again, the NRCS curve number method, as it's called, CN method, it's very popular. Again, it's fairly simple. And the method essentially computes the cumulative runoff depth in inches, given the cumulative precipitation. So yesterday we talked about accumulating precipitation as a function of time for design rainfall events. We could do the same for observed rainfall events. So P of T is the total depth of rainfall water. R of T is the depth of water in inches that is actually becoming runoff. Okay. Then S is called as ultimate abstraction. So this is essentially the losses that would occur if the rainfall occurred for an infinitely long time and all the storage capacity of the soil was exhausted. Okay. So that is S, the ultimate abstraction. This S is computed as 1000 over Cn minus 10, where Cn is the curve number. And the curve number then reflects the properties of the soil, what kind of land use we have, and so on. Notice that when we are using this expression, we have to be very careful with the units. The total depth of precipitation must be in inches. Ultimate abstraction is also in inches. And the cumulative runoff depth is also in inches for us to use this expression. So this is how the method works. We look at our watershed area, contributing area, find out what the curve number should be, compute what the ultimate abstraction S is, and then for a given rainfall event, whether it's a design rainfall event or an observed rainfall event, at any given time we find the total cumulative precipitation and use this expression to find the cumulative runoff. The one caveat is that the cumulative precipitation P of T must exceed 0.2 S, which is called as initial abstraction. So a certain amount of moisture deficit or deficit over the watershed has to be satisfied by the rainfall before we will have water available for runoff. And that is expressed by this quantity. So if the cumulative rainfall is less than 0.2 S, we will have no runoff. It will be 0. It's only when P of T exceeds 0.2 S that we use this expression. So the first part then is how do we determine Cn, the curve number? And for the curve number, we first start by looking at the soil types for the area that we are interested in. The soils all over the world, in fact, have been classified into 4 groups, A, B, C, and D. And for these different soil types, A, B, and C, and D tell us a little about the nature of the soil. Soils of type A are very high infiltration rates, and they can absorb a lot of water, whereas soil types D are very tight, clay soils, very little infiltration. So the soil type will obviously say how much of the rainwater is going to soak up into the soil versus what is available for runoff. So A, B, C, and D, all soils have to be classified into these groups. So for instance, we have extensive tables. I'm not sure you can see any details over here, but this table, first part, shows all the soils in Indiana and what soil groups they belong to. Similarly, table 2, which is continued, show all the other soils and what soil group they belong to. So given the nature of the soil, we have tables that show which soil group it belongs to. And then we go to tables that I hope you are able to see. The font is small. I apologize for that. And then for urban areas, depending on the land use that we have and depending on the soil type, we typically pick the curve number C sub n or Cn. Similarly, we would have tables for agricultural lands, where again, knowing the kinds of soil cover that we have and knowing the soil type and the hydrologic group, we would pick a curve number. And then we are able to apply the curve number method. The curve number method can be applied for both design rainfall events and for observed rainfall events. The method remains the same. So we will look at a quick example or the steps that are first used, where we use the curve number method to get the time distribution of runoff now from a watershed. So the first step is to determine the composite curve number. So if we have a large contributing area which is heterogeneous, we divide it into homogeneous parts. For each homogeneous part, we first estimate the curve number, and then for the entire contributing area, we compute a weighted curve number or a composite curve number based on the areas. Then we determine the cumulative rainfall depth as a function of time. This is what we call as capital P of T. For design rainfall events, we will, given rainfall depth and duration, we determine the time distribution of cumulative rainfall, for example, using Huff curves, as we talked about yesterday. For observed rainfall events, of course, we have observations, so we can determine the cumulative rainfall depth from the observed data. We would divide the entire storm duration into convenient intervals. So to basically do the calculations, and this term convenient intervals is actually quite important for calculations that we will see later. So for a given storm event, we can determine the cumulative rainfall depths at the start and end of each interval, whether it's an observed event or a design event. We can use the curve number method to determine cumulative runoff depths, again at the beginning and end of these time intervals, and then we can take successive differences to compute the runoff values. Okay, so these are the steps that we would use. And this is a schematic diagram. So for instance, let's say this is the total rainfall hydrograph, and we divide it into convenient time intervals, delta t's, as shown over here. And then what the curve number method tries to do is, given, let's say, this red curve, which would be the area under this shaded portion for the total precipitation, after initial abstractions are satisfied, so when 0.2 times S of precipitation has occurred, we will then start having runoff. And what the curve number then is trying to do is, given this rainfall event, compute P of T and then compute R of T cumulatively as a function of time. So initially, before runoff starts, we have initial abstractions. Then as rainfall continues, some of it continues as losses or continued abstractions. The rest of it is effective rainfall. And it's the effective rainfall depths that we are interested in. So for a quick example, let's say we are looking at a 50-year, 2-hour design rainfall for Indianapolis, and we have a basin which is divided into 4 sub-areas. Each of these sub-areas has a certain soil type. This is the land use, describes the practice and the condition, and the individual areas of each of these sub-areas are provided. Okay. And what we would like to figure out is what is going to be the cumulative runoff and the total runoff depth for this design rainfall event over such a watershed. So we would first determine the composite runoff coefficient. So for each of these sub-basins, knowing the soil type, we can see the soil classification, and knowing the land use and using appropriate tables, in this case, the stormwater manual that is shown below. We have the curve numbers, we compute the composite curve number, C sub n. Once we have C sub n, we compute S, the ultimate abstraction, which is simply 1000 over Cn minus 10. So in this case, that is 3.37 inches. And then if we wanted to find the total runoff depth, so for that entire rainfall event, we have the total P of T as 3.22 inches. We computed S as 3.37 inches. We can use this expression and say the total runoff depth is 1.096 inches. So out of the 3.37 inches or 3.22 inches that fell, only 1.096 inches of that depth is available for runoff. So you have to imagine 1.096 inches sitting over this 210 acres of total watershed area. That volume of water after appropriate conversion is approximately 835,200 cubic feet of water. Okay, so this is a simple computation. Then if we look at the design rainfall properties, we had a rainfall duration was 2 hours. We had a rainfall depth of 3.22 inches. A composite curve number we calculated as 74.81. S was 3.37. Initial abstraction, which is 0.2 S, is going to be 0.67 inches. And then we can use this expression, the curve number method, to create a table of this sort, which allows us to find out how to partition the rainfall into excess, the total rainfall into excess rainfall, and how to allocate it in time, in this case for a design rainfall event, using half ordinates. So we use the same method. Half ordinates were given to us in 10% chunks of time. This was, so 10%, 20 minutes, and so on. Sorry, 12 minutes, 24 minutes, 36 minutes, all the way to 2 hours, 120 minutes. The half ordinates are picked out from tables for first quartile because the duration is less than 6 hours. We pick out the half ordinates, and therefore, as a function of time, we essentially have the cumulative amount of rainfall depth. From the cumulative rainfall depth, as a function of time, we can compute what the cumulative runoff depth is going to be. And you will notice that, after the first 10 minutes, we still do not have any runoff because the cumulative rainfall has to exceed 0.2 S before you'll have any runoff. And we compute runoff then as a function of time. And we can then compute the incremental rainfall depths by taking, successive differences for rainfall. And we can compute incremental runoff by taking successive differences for the rainfall, cumulative rainfall values. And again, this is what we are typically interested in, the last column, which shows over each of these 10% chunks of time, how much rainfall excess is available to move on the watershed as runoff. Okay. So we come over here, and this is simply plotting that same information. What it is showing is in each 10% chunks of time, so 12 minutes, 24 minutes, 36 minutes, how much was the total rainfall in blue and how much was the runoff out of that total rainfall in that time segment. The first time segment, we did not have any runoff. And then we start having runoff, which does the runoff depth, which starts varying as a function of time. So what we are able to do from the curve number method is actually only calculate the runoff depth as a function of time. So it only works with the rainfall hydrograph, whether it's a design rainfall event or an observed rainfall event. And from these, it is able to then partition that rainfall into effective rainfall. So this effective rainfall that is sitting on the watershed, we want to talk about, well, how do we translate that to become stream flow? Okay. And there are several ways to do this. We will talk very briefly about perhaps one of the more popular ways of doing it for runoff estimation using unit hydrograph theory. Okay. And again, these are fairly common concepts, but are used in design, and we'll see design examples, I think, a little bit later, and perhaps some tomorrow also. So let's talk about hydrographs. We have used the term hydrographs already. It's simply a graph of flow rate as a function of time. Typically, a hydrograph will have many components. First, there is direct surface runoff. So this is the part that we are typically interested in. This is when we have precipitation, either rainfall or snow melt, which is the part that is moving on the soil surface, reaching the streams and creating a rise in stream flow. That's the water that we would like to manage. Interflow is the water that is moving in more shallow soil horizons. It can move reasonably fast and could reach the stream, at a perhaps slower rate, but still enough to be associated with the rainfall event. Groundwater or base flow, this is essentially the slow, steady contribution to the stream. And this water might have essentially arrived on the land surface several months before it shows up in the stream. So it basically travels through the soil, reaches the groundwater, slowly reaches the stream, and it maintains the stream during dry seasons. However, it's rain that has arrived uh, much in advance. We don't have to worry about flooding events from base flows. There is of course some channel precipitation, rain that's falling directly on the channel surface itself, that will immediately become part of the stream flow runoff. But the stream flow area is much smaller, much smaller than the watershed area. So most of the stream flow that is generated from a rainfall event is water that's collected over the watershed and is funneled through the stream network. Parts of a hydrograph, again, fairly standard definitions. We have essentially first base flow, then because of a rainfall event, stream flow will start to rise. We will have a rising limb. It may have a flat portion depending on the nature of the rainfall and what the antecedent conditions are depending on the nature of the watershed, a flat or a crest portion. And then once the rainfall event is over, the stream flow will subside, we'll have the recession limb, and it will perhaps slowly reach back to what it was before rainfall starts. When we talk about hydrographs and how to compute hydrographs, we talk about partial equilibrium hydrographs and equilibrium hydrographs. So if we have a watershed and let's say we have a rainfall of constant intensity but infinite duration, just as a concept, or a very long duration. So that is curve A. And we will assume that stream flow starts from 0. And because of the rainfall event, slowly the stream flow is going to rise and eventually it will reach its peak value. And if the rainfall continues, then the peak value is maintained, which means all the deficits that we have, the moisture deficit, depression storage, have all been satisfied. Infiltration is occurring at its equilibrium rate, and therefore whatever the effective rainfall is that is arriving, that is essentially coming out as stream flow. So if I was to normalize the stream flow with respect to area of the watershed, then the effective rainfall and the stream flow discharge would essentially be the same. Now, if the rain were to stop after this equilibrium value is reached, sometimes we call that as T sub P, which is the time for the hydrograph to achieve its peak value. If the rain were to continue and then stop after the peak value is reached, that means then again the stream flow would die down and would have this curve B. However, the hydrograph did achieve its peak value. If basically we have a rainfall event of a, let's say, duration T sub R1, which is less than this T sub P value. So the hydrograph increases as stream flow rises, reaches its peak value, and when the rain stops, it doesn't have the opportunity to keep increasing anymore. And so after a small lag, it will then start to die down, and you'll have a hydrograph of the shape of curve C. And then we would call that as a partial equilibrium hydrograph. Okay. So for this equilibrium state to be reached, the rainfall typically has to have a constant intensity so that everything is in balance. Whatever effective rainfall is occurring, that is coming out as direct runoff. It must have sufficient duration. That means its duration has to be long enough, let's say greater than T sub P, to achieve this peak value, where effective rainfall rate would be equal to the runoff rate. Okay. Let me talk about types of hydrographs, since these become important for design. Natural hydrographs these are the hydrographs that are obtained directly from flow records and measurements. So streams, we have stream gauging stations. Typically, we measure the depth of water, and then we have a rating curve which translates this depth to a flow rate. So these observed hydrographs are very useful because these are what we use to calibrate computer models for both peak flow rates and volumes. We perform flood frequency analysis and so on. And these are also used for other purposes. We define a unit hydrograph, and that's going to be important for us. A unit hydrograph can be a natural or a synthetic unit hydrograph. So by definition, a unit hydrograph is generated when we have 1 inch or 1 unit of direct runoff. So effective rainfall has to be equal to 1 inch. So direct runoff, so this is the amount of rain that becomes runoff after all losses and infiltration have been accounted for. So 1 inch of effective rainfall excess, or 1 unit if we are working in millimeter per hour units. We talk about dimensionless unit hydrographs. So dimensionless unit hydrographs are unit hydrographs, however, they have been non-dimensionalized. So the vertical axis, the flow discharge, is non-dimensionalized, typically with respect to the peak flow rate. And similarly, the horizontal axis is time, that is also non-dimensionalized, typically by using the time to peak as your scaling variable. And dimensionless unit hydrographs are going to be important. I think for design purposes, we are primarily interested in what are called as synthetic unit hydrographs. So these synthetic unit hydrographs are generalized unit hydrographs, typically dimensionless. And these are generalized in the sense that these are developed by looking at data from many, many different watersheds and developing relationships, showing that knowing something about the watershed, we are able to say what the hydrographs should be. So synthetic unit hydrograph is a hydrograph that is applicable to many, many different watersheds. And therefore, it is specialized for different watersheds. And that is what is typically used for design purposes. Okay. So we will talk a little about unit hydrograph theory as a method for translating excess rainfall to direct runoff. So I'm again back to the same picture. What we are trying to do then is, for design purposes, we are trying to figure out how the stream flow is going to respond at our design location for rainfall events, whether they are observed rainfall events or design rainfall events. So if we are given a rainfall event, we first find out what is the excess rainfall. So that is the portion of rainfall that is contributing to runoff after all losses such as infiltration, depression storage, other storages, evapotranspiration, everything has been taken care of. The curve number method was one method of trying to do this separation and get us to excess rainfall. This, of course, is neglecting things like evapotranspiration. And if we are looking at an event-based design, then the duration is short enough that ET and other losses are neglected. We are trying to relate that to direct runoff, which is water from rainfall that eventually reaches the stream and to the point under consideration. So direct rainfall is the result of this rainfall excess. So if I have total stream flow, I have to have a method for separating out base flow, and therefore I know what the response of the watershed is to this rainfall event, and that is direct runoff. So unit hydrograph allows us a method of translating this excess rainfall into direct runoff. So again, the same definition for a unit hydrograph. A hydrograph that is generated, a direct runoff generated hydrograph resulting from 1 inch, 1 centimeter, or 1 unit of excess of effective rainfall. This effective rainfall must be distributed uniformly in space and time and has a specified duration. So the idea is, now we are talking about this shaded portion of rainfall intensity, but this is rainfall excess, no losses. It will have a certain duration delta D, and this delta D will become very important. Since the total rainfall excess is 1 unit, let's say 1 inch, this shaded area must be equal to 1 inch, and therefore the height or the intensity of this rainfall excess is 1 over delta D. So that 1 over delta D times delta D gives you the product 1 inch. So inches per hour multiplied by hour gives you 1 inch. This 1 inch of excess rainfall for a duration of delta D, the direct runoff resulting from that is the unit hydrograph. So you have to imagine this 1 inch of rainfall excess that is allowed to sit on the watershed. It accumulates over a period of delta D, and it flows out at the outlet. It creates a hydrograph. That is our unit hydrograph. So the unit hydrograph will typically be expressed in, let's say, cubic feet per second, because it's a flow discharge. But if I divide by the area of the watershed and do the appropriate unit conversion, I can express it in the same units as the effective rainfall, inches per hour. And therefore, sometimes you see flow rates expressed as in length over time units to make it comparable to rainfall. So this area that you now see under the curve, if it's also given in inches per hour after normalization, since this is the response of this in unit excess, this shaded area must also be equal to 1 inch from mass conservation. So delta D times this intensity, that is a unit excess, and this is a unit hydrograph. So obviously, when we talk about unit hydrograph, the unit rainfall excess, we can have many of these. We have two examples, A and B, of unit rainfall excess. Case A, as you can see, has this shape. It has a smaller delta D, smaller duration, and therefore higher intensity, so that the excess is still equal to unity. Similarly, case B has a larger delta D, larger duration, smaller intensity, but the area is still equal to 1 inch, let's say, unit excess. And the runoff hydrograph or the unit hydrograph for these different rainfall excesses, even though the total value is 1, because their durations are different, they will result in very different looking direct runoff hydrographs. So delta D, the duration of the rainfall unit excess, becomes very important. So if I were to keep decreasing this delta D, the duration of rainfall excess, I would have to keep increasing the intensity so that the total area remains unity. And in the limit, if I were to make the duration go to 0, then the intensity would have an infinite value, but the total area under the curve is still 1 inch. And in that case, we would call that as an instantaneous unit hydrograph. So it's a limiting hydrograph where we assume that, let's say, the watershed surface is initially empty of water, and instantaneously we put 1 inch of rainfall excess over the entire watershed. And then this water will drain out of the stream outlet at the gauging location and create a hydrograph. That would be the instantaneous unit hydrograph. It's a theoretical concept, but also very useful for design purposes, because once we have a unit hydrograph, whether it's an instantaneous unit hydrograph or a hydrograph for any delta D, we are able to translate it to any other duration. Okay. The next slide essentially tries to say what it is that we do with a unit hydrograph. We use the principle of linear systems theory, where we can apply superposition. Superposition allows us to do two things, a linear system theory. First, it allows us to scale responses. And the second thing it allows us to do is superimpose responses. So what do we mean by scaling responses? Well, let's say this is the rainfall excess hydrograph. So we had an observed rainfall event, we used the curve number method, subtracted all the losses, and then the excess rainfall is what is shown over here. So in this case, delta D, the time interval is half an hour, 0.51, 1.52, and so on. In the first half hour, the total excess, we had 2 inches per hour as a rainfall intensity, so 2 times 0.5. So in this first time interval of half hour, delta D interval, we got 1 inch of excess. Similarly, in the second half hour, we got 0.5 inch. In the third half hour, we got 1.5 inches. And in the fourth half hour, we got 1 inch. So let's say this is our rainfall excess. By some mechanism, let's say we have determined what the unit hydrograph is for this watershed when the duration of rainfall excess is half an hour and the excess is 1 inch. This is the unit hydrograph. So this is a synthetic example. So the unit hydrograph that is generated for 1 inch of rainfall excess over a duration of half an hour is given by this. So it's 0 at after half an hour, it becomes 20 CFS. After 1 hour, we have 40 CFS, 1.5 hours, 30 CFS, 20 CFS, 10 CFS, and 3 CFS. So this is the hydrograph that's generated for the synthetic watershed. What we do in unit hydrograph calculations is indicated in this table over here. So we divide time into exactly these delta D time intervals, 0.51, 1.52. So all calculations must be done at these delta D intervals. And then we note down the unit hydrograph ordinates at those values. So 0, 20, 40, 30, which is essentially the shape of this hydrograph at these half-an-hour intervals. And then we create a table where we note the rainfall excess in different columns. So in the first half an hour, the rainfall excess is 1 inch. In the second half hour, the rainfall excess is 0.5 inch. Third half hour, 1.5 inches. And in the fourth half hour, in the synthetic example, we have 1 inch. Okay, we have noted those below. So now we will first use scaling. If this is the response that we have, if this is a stream flow for 1 inch, whatever the excess is, we will multiply it with these ordinates. So when the excess is 1 inch, scaling says if I got 0, 20, 40, and so on, I'll multiply these values by 1. So this is the hydrograph, this column, generated by 1 inch of rainfall excess. If the rainfall excess is 0.5 inch, we simply take 0.5 and multiply it with these values because it's scalable. And so for 0.5, I'll get 0. For 20, I'll get 10. For 40, I'll get 20. For 30, I'll get 15, and so on. But we also note these and start them at delta D time later, half an hour later, because the second pulse of rainfall arrived half an hour later. So its effect at the outlet is also going to be arriving half an hour later. It gets staggered in time. Similarly, the third pulse, 1.5 inches, which is noted over here, we use 1.5 and multiply it with the unit hydrograph ordinates, and therefore get the hydrograph corresponding to 1.5 inches excess. And similarly, for the last pulse, 1 inch, we essentially get the hydrograph from this rainfall excess, and we note it over here. So for different kinds of rainfall excesses in each of these half an hour durations in this example, we have the corresponding hydrographs, and they have been staggered in time. So this part is the scaling part. It's linear scaling. We know the response for unit excess, so response for any other excess is simply scaled. And we have in time. The superposition says that the total stream flow that we observe at the outlet is going to be the combined effect of each of these pulses. So if I look at some time, let's say 1.5 hours, the first rainfall pulse, the stream flow is 30 CFS. Because the second pulse of rainfall, it's 20 CFS. 30 CFS from the third 1.5 inch pulse, and 0 from the fourth. So we can simply add those up, and that's going to be the total stream flow at that time. So this is superimposing the effects of the rainfall pulses to get the total stream flow. At some earlier time, let's say at 0.5 hours, we only have the effects of the first two pulses because the subsequent pulses have not occurred as yet. And so now we are adding horizontally over these rainfall excesses to get the total stream flow. So the rightmost column then gives the direct runoff, which is corresponding to this rainfall excess. And this is time. So we can plot the direct runoff hydrograph as a function of time. So this is, in simple terms, the mechanism for unit hydrograph theory, how, let's say the nuts and bolts of it work. The important part, of course, is how to get the unit hydrograph for our area of interest. So if we are trying to design at a particular stream location, we have a contributing area, we know the watershed. How do we get the unit hydrograph for the watershed? I think that is what the design part then becomes. The rest of it is straightforward. Whether it's a design rainfall event or whether it's an observed rainfall event, we would have to use some method, for instance, the curve number method, to find out what the rainfall excess is. And then we would implement this technique. So how do we do this for design purposes? There are multiple ways. And perhaps I'll talk about the popular ways that are used. I talk about the synthetic unit hydrograph, and that is what is very popularly used. So the NRCS, which is the Natural Resources Conservation Service, previously the SCS, has observed data from several watersheds and provides us with these synthetic curvilinear or synthetic unit hydrographs. The synthetic unit hydrograph looks like this. So this is a generalized unit hydrograph shape, okay? This shape that you see is fixed. So this is dimensionless discharge. So it's flow rate divided by the peak value versus dimensionless time, time divided by the time to peak. So when dimensionless time is 1, that is when the peak of the hydrograph occurs, and in dimensionless terms that's also equal to 1. So the shape of this synthetic unit hydrograph is completely fixed. That never changes. And this is simply a mass curve. It's integrating the area under the unit hydrograph. So it starts and will eventually reach 1 because it's a dimensionless unit hydrograph. So this is a generalized unit hydrograph. And for a given watershed, we would have to take this unit hydrograph and specialize it for our watershed. It is dimensionless unit hydrograph as flow rates and times are scaled with respect to peak flow and the time to peak respectively. So this shape is prescribed, and what this table is showing are the ordinates of this synthetic unit hydrograph. So T over T sub P values and the corresponding Q over Q sub P values. Okay. So this is a synthetic unit hydrograph. This shape is completely fixed. Since it's a curvilinear unit hydrograph, calculations are a little more difficult, but can be done routinely. To simplify matters, we also have a triangular unit hydrograph, only because triangles allow us to compute areas and so on much more easily than some curved shape. So the triangular unit hydrograph is also a synthetic dimensionless hydrograph. Its shape is also fixed. And so this is the triangular unit hydrograph, goes from 0 to 1, 0 to 1 during the rising limb. When dimensionless time is 1, the dimensionless peak discharge is equal to unity. And then this is the mass curve for this triangular synthetic unit hydrograph. Again, these shapes are fixed. And then what we would typically do, excuse me, a triangular unit hydrograph is SCS allows us to work with these triangular unit hydrographs in a simple fashion. Sorry. So this is again the triangular unit hydrograph. This is time. Time to peak is the time it takes to reach the peak value. The recession time, the recession limb is longer, so this is T sub R. T sub P, the time to peak, and T sub R, the recession limb, both of these add up to provide T sub B, which is the time base of the hydrograph. Q sub P is the Q peak value of this triangular unit hydrograph. We imagine that we have unit amount of rainfall excess of a certain duration delta D. So this is delta D. We have unit amount of rainfall excess. L prime is the lag. The lag is the time duration measured from the centroid of the rainfall excess all the way to the peak value of the hydrograph. So it starts at delta D over 2 and essentially goes all the way to T sub P. That is the peak. What the unit hydrograph says, or SCS unit hydrograph says, is the time base of the hydrograph that you see this whole time base T sub P plus T sub R, that's going to be 2.67 times T sub P. So we have T sub P over here, the rising limb, T sub R, the receding limb, is 1.67 times T sub P, and therefore the time base is 2.67 T sub P. So these shapes are fixed by the synthetic unit hydrograph. So some other rules that the synthetic unit hydrograph has, because it's triangular unit hydrograph, we can easily calculate the total area under this hydrograph. And since it's actually flow rate versus time, that translates into the total volume of water that's coming out for unit amount of excess if you factor in the area of the watershed. And so we are able to do a mass balance in this case. So Q prime, which is the total volume, that is simply the sum of these two smaller triangles. So T sub P and T sub R, now all the times are going to be in hours, and all the flow rates are going to be in inches per hour because the units have to work out. So if we make this, if we equate these two and factor in the area of the watershed, then we get an expression for what the peak value should be, because Q sub P over here, if that is in CFS, then we get an expression which says Q sub P is 484 times the area of the watershed, has to be in square miles, divided by T sub P, which is the time to peak. Volume, this is the volume of the water in the hydrograph. If it's a unit hydrograph, this quantity can be written as Q prime over here, because this is essentially the area of the triangle, which is the same as the volume. If that is supposed to be 1 inch, then for a unit hydrograph, Q sub P in CFS, 484 is a conversion factor. A sub M is the area of the watershed, and T sub P is the time to peak. So for a synthetic unit hydrograph, one of the information that we need is the area of the watershed that we are looking at. Some other empirical relationships. For the triangular unit hydrograph, the SCS method or the NRCS method, synthetic hydrograph, also says that the lag that you see, which is this particular duration from the centroid of rainfall excess to the peak, is typically equal to 0.6 times T sub C, where T sub C is the time of concentration for the watershed. Okay. And then delta D is essentially defined in terms of T sub P as T sub P over 2 plus L prime. So delta D over 2 plus L prime was 0.6 T sub C. So once we have that expression for T sub P, we can go back to the previous slide. The expression for Q sub P, we have now replaced it by delta D and T sub C to express T sub P. We have another empirical relationship which says T sub C plus delta D over here must be equal to 1.7 times T sub P. And therefore, we are able to simplify these relationships to say that delta D therefore is equal to 0.133 times T sub C. So what does all this mean? A lot of empirical relationships. The synthetic unit hydrograph, that shape is fixed. So what the method says is, for a given watershed, we need to know the area of the watershed in square miles. We also need to know what is the time of concentration. We talked about the time of concentration, and I said that's going to be very important, not only for the rational method, where it is used for the duration of the rainfall event, but even for unit hydrographs. Once we compute the time of concentration is going to reflect the roughness properties, the nature of the land, the slope, and so on. Once we have the time of concentration, we can compute delta D. Now this delta D is the duration of rainfall excess. And once we compute delta D, that is fixed. So all calculations have to be done at delta D intervals. So we know the area of the watershed and we know the time of concentration. These are the two watershed properties that we need to know. Once we have those two, we compute delta D from here. Once we have delta D and the time of concentration, we can come to this expression and compute Q sub P, which is the peak. We can compute T sub P as well. T sub P is given by this expression in terms of delta D and T sub C. So notice that once we have the area of the watershed and the time of concentration, we are first able to compute delta D. We are then able to compute T sub P, and then we are able to compute Q sub P. T sub P was the time to peak. Q sub P was the peak flow rate. Once we have these two, then the synthetic unit hydrograph can be scaled back to the unit hydrograph, because these are the two scaling values. And we have delta B, so we essentially obtain the unit hydrograph. Okay, and that allows us then to do the storm hydrograph. So let's look at some of the steps for computing unit hydrographs first. We estimate the time of concentration T sub C and the area of the watershed in square miles, just to keep our units consistent. We determine the peak runoff rate and time to peak, setting Q prime, because it's a unit hydrograph, set it to 1. So once we have, let's say, the T sub C, we come over here, compute delta D, which is 0.133 times T sub C. We compute T sub P, which is delta D over 2 plus 0.6 T sub C. Once we have T sub C, we compute Q sub P, the peak value. Then we determine the points on the unit hydrograph from the table for curvilinear unit hydrographs. And we can check that the volume of water on the unit hydrograph will actually correspond to 1 unit of rainfall excess. If you are using the triangular unit hydrograph, then it's fine. We also already have computed T sub P. We know the Q sub P value. The time base is known to be 2.67 T sub P. And therefore, we are able to basically get the ordinates of the unit hydrograph. And then we can use something very simple, numerical integration, using trapezoidal rule or some such to compute the volume of water under the unit hydrograph. And that should equal to 1 inch times the area of the watershed. If the delta T time step is not constant, then you have to use the proper expression. But this is simply numerical integration. Oops. Okay, and then we can compute the storm hydrograph from the unit hydrograph. So one method would be to estimate the basin area using the curve number method, cumulative rainfall, estimate the estimate the basin area, the curve number for the watershed, cumulative rainfall is a function of time, whether it's a design rainfall event or an actual observed event, and estimate the time of concentration. Then we need to do computations at exactly delta D time intervals. So we calculate the cumulative rainfall and unit hydrographs at delta D time intervals. We calculate cumulative runoff and incremental runoff depths, again at delta D time intervals using the curve number method. We compute the storm hydrograph using superposition method. And then again, we check for volumetric balance. So compute the total volume of water leaving the design point with the total the rainfall excess volume that we got from this, from the rainfall event. Okay, we'll quickly go through an example to see how it's done in practice, and I'll stop with that after the example to see if we have any questions. So in this example, I'm looking at a basin in South Bend, Indiana. Its area is 300 acres, so that's 0.47 square miles. The weighted curve number is determined to be 84. I'm going to use a design rainfall event, 2 hours duration, 50-year return period, and I want to use a unit hydrograph. I am asked to assume that the water travels 9,000 feet on unpaved surface with a 1.6% slope. Okay. So the area of the watershed is given, the composite curve number is provided to us, the travel distance is provided, the slope is provided, it's an unpaved surface. So first I can compute the time of concentration. Time of concentration has to be computed based on any of the methods that we have talked about. So in this case, we will use the unpaved surface expression. So for this, given the slope, 0.16, we essentially see what the nature of the surface is. It's unpaved, come down, pick up a velocity of 2 and say, okay, 2 feet per second is the velocity. The travel distance is 9,000 feet. So my travel time or time of concentration in this simple example is 75 minutes. So once I have the 75 minutes, I first determine delta D, 0.133 times T sub C, which comes to approximately 10 minutes. So now all calculations have to be done at 10-minute intervals. I compute time to peak, T sub P, which is delta D over 2 plus 0.6 T sub C in this example, comes to 50 minutes. I can compute Q sub P from that expression. Knowing T sub P, it's 274 CFS. So I have delta D, the duration 10 minutes, T sub P is 50 minutes. This is 274 CFS is the peak. So I can then compute my unit hydrograph. So I go to the synthetic unit hydrograph. Notice for different T over T sub P values, Q over Q sub, the T or T sub P values, the Q or Q sub discharge ratios are fixed. But if T sub P is 50, then T over T sub P is known. I can multiply all of these by 50 and I'll get actual time. Similarly, I have Q or Q sub P value is fixed. Q sub P, the peak value was 274 CFS. I multiply all of these by 274 and get the discharge over here in CFS. So this is time and this is discharge. Time in minutes, discharge in CFS. So that is my unit hydrograph for this watershed. My next step is, of course, to do the volumetric computations. I have plotted the unit hydrograph over here, used trapezoidal rule, and compared the total volume the area under the hydrograph, if that is indeed equal to that 1 inch of rainfall excess over the entire watershed area, and see if those two volumes are equal. So 24.91 acre feet versus 25 acre feet. So it's reasonably close. There will be some error because of how accurately I'm computing the area under this curve using numerical integration. The next step is to look at the design rainfall. So the design rainfall, in this case, we are going to use regression equations. We were essentially told that the duration is 2 hours at the 50-year rainfall intensities. That's what we are essentially using. And for South Bend, basically the rainfall intensity is 1.36 inches per hour. So using the regression coefficient C, alpha, D, and beta, return period of 50 years, rainfall duration of the design duration of 2 hours, it's 1.36 inches per hour. So for the 2-hour duration, the total rainfall depth would be 2.72 inches. So this is our design rainfall event. 2.72 inches is the total rainfall depth. So incremental rainfall depth is what we need to compute. Runoff depths are what we need. And now we have to be careful about how we do the computations. Because delta D was 10 minutes, our time axis has to be in 10-minute intervals, 10, 20, 30, and so on. The total percentage of storm time for 2 hours, 120 minutes, corresponds to 100% of the time. So 10 minutes corresponds to 8.33, 20 minutes corresponds to 16.67%, and so on. So this is our cumulative dimension time. And then we need to compute the cumulative percentages of total storm rainfall. Now the Huff ordinates are always or were given in a table, as we talked about yesterday, in 10% chunks of time. Those had to be converted now. So 10% chunks of time would be 12 minutes, but we have to interpolate them to get to these 10 minutes. So we do that and create cumulative percentage of total storm rainfall by interpolation of Huff ordinates. And then we can compute the cumulative runoff. So this is the cumulative rainfall, 100% corresponds to 2.72 inches. Therefore, 16.66 is 0.45 inches, 33.34 is 0.91 inches, and so on. So this becomes cumulative rainfall. Okay, I request everybody to mute mute themselves if they're having conversations. Cumulative runoff, then I'll use the curve number method here. I have got the cumulative rainfall. I use cumulative curve number method, compute the cumulative runoffs, again at exactly these delta D time intervals. And from these cumulative runoff, I'll take successive differences to figure out what is the rainfall excess in each of these delta D time intervals. And that is my final column over here. So this is what I now need to use and combine it with my unit hydrograph to be able to do the storm hydrograph. Okay. And then we get a large table, which I'm not sure you'll be able to see because of the screen size. But what we have on the leftmost column are the unit hydrograph times in 10-minute intervals. The time ordinate, unit hydrograph ordinates over here also in 10-minute time intervals. And then all the rainfall excesses that we got are listed over here. For each of these rainfall excess, I scale it with respect to the unit hydrograph ordinates and get this column over here. Similarly for successive rainfall excesses, and again, they are going to be staggered by this delta D time interval. And then to get the storm hydrograph, I then add up horizontally to do the superposition and therefore get the final storm hydrograph. Okay. So finally, we are able to plot the storm hydrograph as a function of time, which is what I have in my final slide over here, is a storm hydrograph as a function of time, which allowed us to convert this design rainfall event over this watershed into what a stream hydrograph would look like. Okay. So these are the topics that I wanted to cover for today and leave some time for questions. Again, request everybody to mute. So we talked about runoff from design rainfall. We talked about the rational method for only computing peak discharge from design rainfall. So the rational method can only be used for design rainfall, can only give you one peak value. And with this, you can actually do storm sewer design and detention storage design, which we may talk about tomorrow. We also talked about runoff from design or observed rainfall events. We talked about the curve number method for separating rainfall into rainfall excess and abstractions. I talked very briefly about unit hydrograph theory and how to develop the storm hydrograph. And in this context, we talked about the SCS triangular unit hydrograph and the SCS curvilinear unit hydrograph. So, I would like to stop over here and leave the rest of the time for any questions or any other discussion that we may choose to have. So, Siva Parvati, is it okay if I stop sharing now?
Yes, sir. Sir, we got one question from the participant, sir.
Just a minute, let me, yeah, go ahead, please.
If you want to quantify the natural discharge from the aquifer, is it sufficient if we are able to separate base flow from flood hydrograph?
I don't know whether it's sufficient or not. I think if you're looking for natural discharge, then if you have base flow, so I'm going to say yes, even though base flow separation is not an exact science. So with base flow separation, even after when you observe, when you have a natural, let's say, stream flow hydrograph given to you, and you use a base flow separation technique, the base flow is not likely to be one constant value. It is going to be changing as a function of time. It will give you an estimate of what you think is base flow, and something else has to be known for us to be to say that is what the aquifer discharge is going to be. Base flow is primarily, I guess, contribution from groundwater flow. So it is related to aquifer discharge. But whether it's an exact same quantity or not is difficult to say.
Sir, one more question, sir. In case of rural watershed, should we consider base flow in hydrologic model?
Yes. In case of rural watershed, perhaps more so than in urban watersheds. Urban watersheds, because of urbanization, they tend to be highly impervious and water is stored. For rural watersheds, especially during dry weather flows, it is being sustained by base flow. Stream flow is sustained by base flow. So I would expect the answer is yes, you should consider what the base flow is.
Sir, where we are going to use the dimensionless unit hydrograph, sir?
Actually, dimensionless unit hydrographs are used for many designs. To get the unit hydrograph for a watershed, for many designs, we need to know what the nature of the hydrograph is going to be. Many regulations essentially say that the entire hydrograph has to be used. For instance, we will talk tomorrow perhaps about stormwater storage. And we will use a particular method. But if I want to figure out for a design rainfall event or for what I think is an observed rainfall event, how much water I need to store, I need to know what the total hydrograph is so that I can figure out how much volume of water I'm dealing with. Just knowing one peak value from the rational method will not allow me to automatically do that. So in such cases, we are required to determine what the hydrograph is going to be. For a given watershed, I will not have data, and I may not have data to say, okay, this is a unit hydrograph for this watershed. But knowing the area of the watershed and knowing the land use, knowing the slope, I can then know the area of the watershed and I can estimate its time of concentration. With these two quantities, I am then able to construct a unit hydrograph for this watershed by using a synthetic unit hydrograph, either the SCS curvilinear unit hydrograph, for instance, or the triangular unit hydrograph. So with that, I'm then able to figure out what kind of response the watershed is going to have to rainfall events, what kind of stream flows I would have to be managing. So synthetic unit hydrographs, the reason they are constructed is because they are heavily used in design.
Yes, sir. One more question, sir.
Yeah.
Can we use ArcSWAT for rainfall runoff modeling of urban watershed?
SWAT for urban watersheds. So SWAT, I have to let you, was primarily designed for rural watersheds. Urban watersheds, I mean, I would be hesitant to use it. It's not my natural choice. It's not my first thought. I would much rather use something like SWIM or some other water model, which is perhaps a little more geared, or can be a little more geared towards urban watersheds. Urban watersheds are a little more challenging, I think. SWAT is not my first choice because SWAT is soil water assessment tool. It was, at least when it was conceived, it was more designed towards, I think, for crop management, long-term water use, and I think it was more geared towards rural or semi-urban watersheds.
Sir, which method is most suitable for estimating runoff in gauged and ungauged catchments?
Which method?
Yes.
Again, so it depends on the nature of the watershed, depends on the kind of data you have, on the kind of analysis that you want to do, how detailed your analysis needs to be. All these will determine whether you will use a simple lumped model or a unit hydrograph model or a much more detailed physically based model, or you'll use SWOT. I mean, I think it's a function of what it is that you want to get out, what detail you're looking for. It could also be driven by what kind of data you have available. So a lot of factors go into determining what is a suitable model to use. It's not that one model is suitable for all applications, for all watersheds, for all purposes. So there is no best in that sense.
Sir, for urban flooding, is kinematic, dynamic, or diffusion modeling? Which of these hydraulic routing is preferred?
So I think SWIM, I mean, those of you who use SWIM, which is, it has these options. Again, difficult to say. I would say if you are dealing with a watershed which has very smooth surfaces and steep slopes, then you are fine using the kinematic method, because that's the simplest and least computationally effective, least computationally demanding, I'm sorry, and it's the kind of watershed conditions are such that the kinematic wave is a very good approximation under those circumstances. If the watershed is more complex, then and you have let's say rougher surfaces, more flatter slopes, then the full Saint Venance equations or the dynamic wave approximations are supposedly the correct ones. However, the dynamic approximation, the equations are more complex. They are much more nonlinear. They're also prone to higher instabilities. They can be prone to issues of convergence and so on. So we do have to contend with that. The diffusive approximation is somewhere in between these two approximations. All the approximations are based on the momentum equation. The continuity equation is, of course, honored by all approximations. The diffusive approximation is used when you think that you are going to have some backwater effects. So the kinematic wave does not allow backwater effects. In other words, water has to, the characteristics as they're called, or water has to just keep moving in one direction. Nothing that is happening downstream can affect any upstream condition. So no backing up of water is allowed and so on in the kinematic wave approximation. So you have to see what kind of watershed it is and whether a kinematic approximation is a reasonable way to go. One test that you can perform is for a given watershed and for a given rainfall event, do the kinematic wave and do the dynamic wave and do the diffusive approximation and see how different the hydrographs are. If they're not very different, then your kinematic wave is good enough. But that's, you know, sort of a quick and dirty or a rule of thumb kind of thing. But the three approximations that the question, you know, whoever asked the question raises, they are talking about different levels of complexity. Kinematic wave, then diffusive wave, then the full dynamic wave. So that's my answer. For an urban watershed, if the surfaces are smooth and if they are steep, the simple answer would be yes, the kinematic wave would be good enough, because water would, you know, there's little chance of any blockages and water backing up and any backwater effects. Mathematically, we would say that all characteristics are only moving in the forward direction, then kinematic wave is fine.
Sir, how to evaluate accurately the apparent runoff coefficients for a catchment?
So this is, so runoff coefficient, that means we are using the rational method. And the rational method is simple, and yet it comes with this, like I said, the entire experience of a modeler has to be encapsulated in how well or how you estimate runoff coefficients. And of course, there is some subjectivity involved, so I cannot say that there is a great method. Most of the time, we rely on tables, which also give ranges for different land uses and different soil types. And if you don't do anything better, you should use middle of the range. If for some reason you think, well, we have a soil type, but you know, I'm interested in conditions where the soil is already wet, so I'm going to use a certain end of the runoff coefficient, you may do so. But I cannot say that there is a standard method of estimating runoff coefficient. People look up tables, and as I said, typically find a value middle of the range as an acceptable runoff coefficient.
Sir, what about the formula regarding the runoff estimation regarding Rives formula?
Okay, I'm not immediately familiar with the Rives formula, so I do not know how to answer that question. There are many methods of runoff estimation, many methods for time of concentration as well. So I do not know the answer to that. I do not. Okay, go ahead.
Sir, how to fix the position of manholes and outfall in the software?
Okay, which I'm assuming you're talking about EPA swim software then, because you're talking about manholes, which are typically features that we see in urban stormwater design systems. I think the way swim and most of the other software work, how to fix them is, this is a two-part question. If I'm doing design, then design regulations state that manholes must be there at all intersections, at all places where the pipe is going to change diameter or change slope. And even if it's a straight stretch of pipe, let's say for a very long distance, we must place manholes at certain frequency or certain intervals, every 100 meters or every 50 meters, because manholes are also access points which are required for cleaning and maintaining sewer lines, whether storm sewers or sanitary sewers. So in terms of design, where they have to be placed, you know, intersections, definitely wherever pipes are changing diameter, wherever there is change of slope, or by regulations, it has to be at such frequency. When we use the software wants to treat we place, whether you call them junctions or manholes, between two junctions or two manholes, two maintenance holes, the software treats that as one piece of pipe. So every place where in a software you would essentially put a manhole or a junction, wherever you think, so you would split up and place junctions wherever you think they need to go. And in between junctions, it's just one piece of pipe. You are not able to change diameters or slopes within the pipe section. I'm not sure I'm answering the question, but so all intersections, wherever pipes change diameters, change slopes, or regulations will say that you must have, even if you have very long straight stretches, they will say you must have manholes at these frequencies. So you should put manholes over there.
Sir, to what extent the soil heterogeneity is incorporated in the SCS-CN method?
Okay. So the SCS curve number method also says, you are looking at a watershed area. And within the watershed area, when you use the curve number method, you are now partitioning rainfall over that entire watershed. We are dividing the watershed into, if it's a heterogeneous watershed, different soils, we will divide it into smaller pieces so that within each piece, we have a homogeneous soil, and therefore we have one A, B, or C, D classification for that soil. And therefore we estimate one curve number for that smaller homogeneous piece, and then we do a weighted averaging of the curve numbers. So the heterogeneity of the contributing area is lumped into one curve number, which is a weighted average, a composite curve number.
So from the participants, if you are having any questions, you can unmute yourself and you can raise your question. Sir, what about the outfall in the software, sir? Fixation of outfall.
Okay, I'm thinking these are either, I'm assuming these are questions on EPA swim model.
Yes, sir, same.
Okay. So the position of the outfall actually is, firstly, if you are designing, then you put the outfall where you think the outfall should be. But typically the outfall is the outer or the last most downstream junction where water is completely being discharged out of the system. And perhaps it's going into a stream or going to a larger body or being discharged on the surface. Usually that has to be done after treatment, but that's the last junction, last downstream junction that is leaving the entire system. So it acts as a boundary condition in EPA swim and says water is allowed to flow out. The reason you can have an outfall is because you are able to place a downstream boundary condition there. In other words, water is flowing freely, or I think you are able to prescribe a outlet hydrograph if you must, and so on. So it's usually the last or the most downstream manhole or junction. That's your outfall.
From the participants, if you are having any questions, you can raise the questions by unmute yourself.
Any other questions? I just wanted to also point out that, you can ask me questions. They don't have to be on what I covered. I designed it, by purpose, to talk about very simple design principles. So that was the goal. We did not talk about open channel flows or some of the questions about dynamic waves and so on. Again, very valid questions, I think, but I also then want to give you a preview, since we have a few minutes of, so tomorrow then I want to talk a little bit about how we can use something as simple as a rational method to do storm sewer design, or how we use it for designing detention storage structures. So some of the things that we have talked about today in terms of the rational method as a method, how we use that to design for design purposes. And as some of the questions reveal, the rational method is not the only method for designing. Sometimes you actually need the full hydrograph. So you need a more sophisticated method to use in design. The rational method, just remember, gives you only one design peak value. And so it has these limitations. It just, the reason for its popularity is it's very simple to implement, doesn't require complex calculations.
Sir, one question from the participant. Any research opportunities at Purdue University in the future?
Yeah, Purdue is a research one university. So research is a very important component of what we do. I do not see universities like Purdue, or many of the universities in India not doing research. The So, I mean, the simple answer is yes, there will always be research opportunities, but what those opportunities are will likely be evolving with time, evolving with our understanding, what we think are societal needs. So all of those will combine to determine research needs. But at Purdue, in the water group, our research is I think some of the research is, of course, in flood and inundation, flood mapping, how to make it accessible to users much more easily. So one of my colleagues, Venkatesh Marwade, works in that area. We have another colleague who works in Great Lakes, very interested in lake hydrodynamics and water quality. That is Carrie Troy. We have another person, Antoine Aubenaud. He also works in water quality and natural systems. We have Professor Dennis Lin, who is more of a sediment transport person. And then I also work in watershed hydrology, contaminant transport, spatial variability, and very interested in machine learning. But with a caveat, I think my interest in machine learning is in hydrologic applications. So typical machine learning that computer science or statisticians do, they deal with extremely large data sets. Whereas hydrology is challenged in a different way. Our data sets are very limited, but very high dimensional. So if, in fact, we're on the other end of the spectrum, our data are very scarce. So what kind of statistical or learning techniques would be applicable to hydrologic applications? I'm interested in that. And I'm also interested in the idea of uncertainty. How do we translate uncertainty? How we use uncertainty into defining not just predictions, but what our prediction limits are going to be. And generally, so research goes on in many different areas.
Sir,
any other questions? Yes.
One more question, sir. Mr. Surender, he has posted a question. I work in the field of flood modeling, flood mapping. Is any postdoctoral fellowships are available in flood modeling in Purdue University?
I think postdoc fellowships, typically you have to reach, I mean, if the faculty has an opportunity to take a postdoc, they may. I think Professor Marwade is the one who does most of the work in flood inundation modeling. You would have to reach out to him individually to find out about whether he is looking for a postdoc. Sometimes faculty will advise, will advertise that they're looking for postdocs in a certain area. Postdocs are, of course, less frequent than graduate students.
Sir, what should be the duration for postdoc, sir?
Well, I don't know what should be the duration. A typical duration is 2 years. The postdoc typically, the duration would depend on what the project is, what you need to deliver, and I think 2 years, 3 years are not unusual. Less than a year is rare. It can happen. But the postdoc is important, I mean, for gaining experience. It's also a bridge between completing your PhD and typically starting as a faculty member at some institution or in a research lab. And so the postdoc time is used to gain experience, build your resume, gain experience for writing proposals, and doing some independent thinking, trying to develop your own ideas, and and basically developing your resume as well.
Sir, if we don't have any questions from the participants, shall we close the program, sir?
Yeah, that is fine with me. I left more time for questions today, but
Yes, yes.
I mean, how much time should I leave for questions for tomorrow?
The last 15 minutes is sufficient, sir.
Oh, 15 minutes. So yesterday 15 minutes was, we went actually quite a bit over. So I left more time today. So 15 minutes. Okay, I'll try and plan for that then.
Yes, sir.
Okay. All right.
Okay, sir. Thank you so much, sir, for your wonderful and very elaborative lecture on all types of hydrographs and their application for estimating the flood water and the stormwater designs. So, thank you, sir.
All right. I hope to see you all in other sessions then. Okay.
Yes, sir.
All right. Bye, everybody.
Okay, sir. Thank you, sir. All the participants, please fill the feedback link. And submit the feedback link. And again, our next session will start at 4 p.m. అంటే ఎలక్ట్రానిక్ సర్టిఫికేట్స్ ఆన్లైన్ లో అవుతుంది.